The Hecke algebra, the module over the long polynomial group Q has two famous bases. It's usually defined in terms of a natural basis of symbols TW, where W is a permutation of set. Multiplication boils down to considering TW times TS, where S is a generator. The formula for TWTS has two cases depending on whether WS is less than or greater than W in the root order. The second basis, due to Pecha Kucha, is defined in terms of a barring relation, which takes root Q to its reciprocal, and TW to the inverse of T sub W inverse. Expanding that in terms of the natural basis, we obtain coefficients known as the R elements. The Pecha basis with elements written CW is barring union. If we modify each element by multiplying by root Q to the length of W, then the resulting elements indexed by 312 avoiding permutations W are just sums of natural basis elements TB with B less than or equal to W in the rule. A linear functional theta of the Hecke algebra to Laurent polynomials in root Q is called a trace if its evaluation at each product D1, D2 is equal to its evaluation at D2, D1. Traces form a vector space, and 6 bases of this trace space correspond to 6 well-known bases of the symmetric functions. 3 of these are character bases, irreducible characters, and sign characters, and trivial characters, which correspond to sure elementary homogeneous symmetric functions. 3 more non-character bases we could call power sum, binomial, and forgotten traces, because they correspond to power sum, binomial, and forgotten symmetric functions. Another trace, delta 1 to the n, maps TW to 1 if the cycle type of W is 1 to n and 0 otherwise. Another trace, zeta n, maps TW to R W, which is summated. The trace theta is determined by its evaluation that elements T U lambda, where U lambda is any minimum length element of the lambda class of SM. To evaluate theta at some element D, we first evaluate theta at all the elements T U lambda, then take a linear combination of these. The lambda coefficient involves the trace function delta lambda, which we can compute first. We saw delta 1 to the n 30 seconds ago. Alternatively, a trace theta is determined by its evaluation of the Pecha Kucha basis elements C V lambda, where V lambda is the longest element of the lambda Young subgroup of Sn. To compute theta D, we first evaluate theta at all the elements C V lambda, then take a linear combination of this. The lambda coefficient involves the modular trace V lambda, which we saw a minute ago. The evaluation of V lambda of CW for any W and Sn is a polynomial Q, gaming conjecture to have non-negative coefficients. It's known that chromatic symmetric functions are related to together trace evaluations. Specifically, given a graph G, we can define a quasi-symmetric function for the proper colorings of G, equated by Q to a statistical coloring. If G is the natural indifference graph corresponding to a 3-1-2 avoiding permutation W, then the quasi-symmetric function is symmetric and is the generating function for evaluation of Hecke algebra traces like a Pecha Kucha basis CW. Expansions in the sure basis, binomial basis, and forgotten basis yield coefficients which are evaluations of irreducible characters, induced sign characters, and induced trivial characters respectively. In the elementary expansion coefficients, we see binomial trace evaluations. The Feynman's conjectured binomial trace positivity implies the positivity of the chromatic symmetry. Related to chromatic symmetric functions by plethism are unicellular LLT functions. These can be parameterized by 3-1-2 avoidance permutations, so that the one corresponding to W is combinatorially defined in terms of arbitrary colorings that is not necessarily proper. The indifference graph corresponds to W. Like the chromatic symmetric function XG, the symmetric function LLTW also is a generating function for evaluation of certain traces of the Pecha Kucha basis element CW. Let's call these traces LLT analogs of the standard bases of the trace space. So expansions of unicellular LLT polynomials in the sure basis, binomial basis, and forgotten basis yield coefficients, which are evaluations of LLT analogs of irreducible characters, induced sign characters, and induced trivial characters, respectively.
That's where you tell a joke.
So we have concise descriptions of LLT and logs that produce assigning to the characters. The deduction from the ends of algebra is H graph. In particular, the LLT analog of the induced sign character is the tensor product of the delta traces indexed by L1s, the induced from H lambda to Hn. The LLT analog of the induced trivial character is the tensor product of the zeta traces once defined for the bar elements, induced from H lambda to Hn. In the special case that lambda equals n, we can also express these characters in terms of reduced formulas involving hook lengths and binomial coefficients come from principal specializations of shear functions. So now we can understand not just chromatic symmetry functions, but also LLT functions from the point of view of Pecha Kucha.
I'm going to tell you 6 minutes worth of about work with Teo Brenti, who's here, Melissa Sherman-Bennett, who's also here, and Ron Tessler. And I'm going to be telling you about some tricolored subdivisions, pictures that look like this. This is a polygon subdivided into smaller polygons, which are black, white, and gray. And from every tricolored subdivision, we will associate a polytope, gamma, and also a cyclic order. This is a cyclic analog of a coset. And we'll explain how the volume of the polytope equals the number of circular extensions of this cyclic partial order. Each tricolored subdivision also gives rise to an identity on the Grassmannian of two planes of n space, and there's also applications to the amplitude, which is a geometric object that arises in physics in the context of scattering amplitudes. So, tricolored subdivision is the main object, and it's this dissection. Okay, so there's a cyclic analog of partial orders and linear extensions, and these are called partial cyclic orders and circular extensions. So you should think of, so as an example, C is a partial cyclic order on the numbers 1 through 8, in which we require that 2, 5, 7 are circularly ordered, 5, 7, 6, and also 1, 8, 7, 2 are circularly ordered. So imagine placing numbers on a circle and reading them in clockwise order. So a circular extension of C is this sequence here, because 2, 5, 7 appear in circular order, 5, 7, 6 appear in circular order, and 1, 8, 7, 2 appear in circular order. And you can read off a partial cyclic order from this tricolored subdivision, where you look at your white polygon, read its vertices clockwise, and you look at the black polygons and read their vertices counterclockwise. So from a tricolored subdivision, you can also define a polytope, a Park-Taylor polytope. And the way it works is that for every compatible arc, I to j, and compatible arc is either an edge of one of your polygons or an arc that lies entirely inside a black or white polygon, we will associate an inequality. So I to j is my compatible arc. Inequality looks like this sum of consecutive x's, xi through xj minus 1, and we give a lower bound and an upper bound to that sum of x's. And the lower and upper bound are related to how much black stuff you see to the left of your arc I to j, and also how much black and gray stuff you see to the left of the arc. So in this example, 2 to 7 is a compatible arc because it bounds the polygon, and it gives the inequality down at the bottom. So every tricolored subdivision gives rise to two things, a partial cyclic order and also a polytope. And the first result is that for any tricolored subdivision, the volume of that polytope equals the number of circular extensions of this partial cyclic order. So this might remind some of you of one of Richard Stanley's papers, and the result of the volume of the order polytope of a coset equals the number of linear extensions. So this is kind of like a circular analog of that story. And it's also related to work of Meyer, Joseph, Vera, Ramaswamy, and Björn, and Usa Morales and Yip. And my student Yuhan Zhang has work in progress extending this theorem to the H star vector. And I think she and Elizabeth Bullock are also working to extend these results to a more general context.
Do you use circular reasoning to get here?
We also get a Grassmannian identity from any tricolored subdivision. So if you give me a permutation W, we can define a Park-Taylor function, which is this rational function defined as 1 over a product of Plugger coordinates. These Plugger coordinates come from our particular permutation. These are Zucker coordinates on the Grassmannian of two planes at n space. And the statement is that for any tricolored subdivision with at least one great polygon, if C tau is the corresponding cyclic partial order, then the sum of the Park-Taylor functions Pt of W, where W ranges over all circular extensions, that sum equals 0. So it's a fun exercise to check that this works, like for a tricolored subdivision of a quadrilateral. Just take a quadrilateral, put one gray triangle and one say black triangle, check it works. And finally, we have applications to this physics object called the amplituhedron. This is a geometric object A and K M of Z, indexed by 3 positive numbers N, K, and M. This object generalizes cyclic polytopes, and in particular, it generalizes polygons. And you can study its tilings. This is an analog of the notion of triangulation. And an observation that we made back in 2020 is that for even M, all of the known tilings of the amplituhedron A and Km have cardinality equal to the number of plane partitions in a related box. And so now, using the previous results I showed you, we can prove that result for M equals 2. So all tilings of the amplituhedron A and K2 of Z have size equal to this magic number, which in this case is n minus 2 choose K. So
So thanks to the organizers for setting this up, even though they're showing no mercy. And thanks to Worley for coming. So I'm going to talk about 4 conjectures involving 2 of Richard's finest ideas. The first of these finest ideas is the chromatic symmetry function. So we start off with a graph and then a proper coloring as an assignment of colors to the vertices so that adjacent vertices get different colors. You can see 2 examples here. Typically, we will use numbers instead of colors to designate the numbers to use the colors. And then to each coloring, we get a monomial. So here we get x1 squared x3 because there are 2 x1s and 1 x3. And then summing those monomials over all proper colorings in the graph, we get the chromatic symmetry function. So we're summing over proper colorings, and then the subscripts here are the colors that are used on the vertices. Okay, so the question is, could you have 2 different graphs with the same chromatic symmetry function? Richard answered this question in his paper, and he gave this example of 2 graphs with the same coloring. And then he asked, we do not know whether XG distinguishes trees. So in other words, if T and U are non-isomorphic trees, do their chromatic symmetry functions have to be different? Lots of people have done work on this. Okay, here's a list, a sample of some of the names. And enough work has been done that we now call this a conjecture, Stanley's conjecture, that the chromatic symmetric function distinguishes trees. So distinguish means if T and U are non-isomorphic, they have different chromatic symmetric functions. I want to bank this spare time for Richard's 90th birthday. Tom, you're keeping a record of how much spare time.
Yeah.
Okay, so that conjecture is pretty well known. Here's one that is less well known and needs should be more well known. I'm going to call this the lower Warrington conjecture. This appears in the paper. So what if we plug in values for the xi? We have this infinite set of variables. What if we plug in values as follows? This is the principal specialization, also appears in EC2 quite a bit. So we said xi equal to q to the power of I for some q variable, some parameter q, and then we said all the other xi's to 0. Okay, so now instead of having a symmetric function in an infinite number of variables, we just have a polynomial q. And their conjecture is that that is enough to distinguish trees. Okay, so this principal specialization, polynomial single variable distinguishes trees. In fact, the data suggests that fewer than n non-zero variables are needed. If you just use q squared, and q cubed, that's enough to distinguish trees on 10 vertices. Okay, how many you need for a particular n is mysterious. Okay, so now we're going to switch into a different setting. We're going to move into the setting of p partitions, another one of Richard's finest ideas. We're going to just restrict the set of strict partitions for the purposes of this presentation. So this is very similar. We have a post-set. A strict p partition means we assign numbers to the elements, so they're strictly order preserving. So along edges, the numbers have to go up as you go up in the post-set. And then the same idea, we assign a monomial to each one. according to the number of appearances of each number. We sum those up, we get the strict p-partition numerator. So it's we sum over all the p-partitions x1 to the number of ones, x2 to the number of twos, and so on. And the question is, what about the equality question in this setting? And again, quite a number of people have studied the equality question for p-partitions. The story is completely parallel, right? So you know what happens in the next two slides. The first conjecture, so this is with my co-author Jean-Christophe Abal and Karen Genevu, but it previously appeared in the form of a question by Sergi and Sergi. So the conjecture is exactly like Richard's conjecture. It says that the strict p-partition numerator distinguishes pointers whose Hasse diagrams are trees. So these in particular would have different p-partition numerators. An interesting comment, this should say conjecture 3. So if you affirmatively answer this conjecture, then you've also shown that the chromatic quasi-symmetric functions of Schrödinger and Maximum, the diagram setting for LZ, those would also be distinguished by those would also distinguish trees. And then all the conjectures I've mentioned here have substantial numerical evidence. Although I'd much rather if people would prove some special cases of these. I think that would be more meaningful. And so there's a lot of scope for special cases. And then just like inspired by the Laura Warrington conjecture, we looked at this, and it turns out it seems to be the case that again, element post-sets are distinguished by this principle of specialization, which is again is a polynomial. And this principle of specialization, in fact, it has a nice interpretation. If we expand it out as a polynomial cube, then these coefficients AIs, these are kind of the number of strict p-partitions that map to n and are p-partitions of I, meaning the sum of all the values is equal to I. And I skipped over a lot of details. If you want the full details are in the paper. Happy birthday, Richard. Next lecture.
Thank you. Okay, I'm going to talk about a permutation problem of Don Puke. So every once in a while, Donald Puke sends me a question, and usually I can't answer them or anything about it. But this is one of the few where I was able to actually solve the problem. And I should also say that I learned about permutation enumeration from Richard, and that was in fact the subject of my thesis way back a long time ago. So Don wanted to count permutations in which every peak and every valley is odd. So the peaks are the positions where the preceding and succeeding numbers are smaller. So 9 is bigger than the 8 and the 5. It's in the 5th position, so 5 is the peak, and 7 is the valley. The number of the 7th position is less than the previous one. So Don also called these permutations up, or down permutations, because they always go up. And in every even position, you're either going up, or down. Okay, so it is actually already known that the exponential generating function for these up, or down permutations of odd length is given by this formula. For even length, it's easy to get the even length from the odd length, so I won't talk about it. And now so what Don was interested in is the number of up, or down permutations that end with a given number. He normalized it by taking the set to be minus n to n, that's 2n plus 1 numbers, and that ended k, so Pn of k is the number that he's interested in. He wanted a generating function for these numbers. So he showed combinatorially that Pn of k satisfies this kind of funny recurrence with an absolute value sum. Well, we need 3 lemmas, which went by pretty quickly. The third one is this formula here. Notice that this is a second difference. So this is a second difference of things. And that suggests that we should look at the first differences. And this 2 is kind of annoying. So to get rid of it, we'll divide by 2 to the n. So now I'm going to define these numbers AMI. They're just the p's. They're kind of shifted a little bit, divided by a power of 2. In the case where m is even, and if m is odd, then they're the first differences of these things. So then AMI satisfies this kind of first difference equation for all n and all I. So that's much simpler. And that means that these numbers a and I form what's called a sidal array. And that means that if you take the difference of two consecutive numbers here, you get the number above it in the middle. So much for that. Okay, so lemma 1, which went by pretty quickly, is this formula, and lemma 2 is this essentially equivalent to this formula. And it turns out surprisingly that knowing that we have a sidal array and those two restrictions, that's enough to determine the generating function, which is given by this expression. And again, this power of 2 is just to make things simpler. Okay, well, Knuth expected a generating function, something more like this, that, you know, it's sort of what you might expect if you've got 2n plus 1 things, so it should have z to the 2n plus 1 over 2n plus 1 factorial, and then a polynomial like this. So why do we get an exponential generating function in 2 variables instead? Well, I'm going to say a little bit about that by just giving some other examples where you have something similar. So the way to think of it that explains why we have an exponential generating function in 2 sets of variables is we think of we're counting permutations of a union of 2 kinds of numbers. These numbers from 1 up to n minus k, these positive numbers, and these negative numbers that end with 0. So I'm shifting things a little bit. And then the 2 variables x and y correspond to the negative and positive numbers. So it's like we have 2 different kinds of sets of labels. And that's why we have a 2 variable generating function. We have similar things where maybe the simplest example of this sort of thing is counting alternating permutations that end with a given entry. The generating function for these is given by this formula. I'm not going to read the formulas, you can read them yourself. And this always gives, I went a little bit too fast. Unfortunately, I missed the bottom half of that slide, but here's another example, the Eulerian numbers. You have a kind of a generalization of Eulerian polynomials that counts permutations according to their last entry. So we want to count permutations of this bunch of negative numbers and some positive numbers that end with 0. And those polynomials are given by this generating function. And when we put them into a 2 variable exponential generating function, we get this formula, which says that they also form a sidal array. So the thing that I went by too quickly was that whenever you have e to the y times some function of x plus y, you get a sidal array.
The goal of this research is to find a nice representation of modular lattices, as close as possible to Birkhoff's representation of distributed lattices. Representing elements of modular lattice as suitably constrained subsets of some base set allows saturated chains in the modular lattice to be represented as tableau by assigning sequential integers to elements of the base set under suitable constraints. Birkhoff represents the elements of the lattice of partitions as ideals of the base set of joint irreducible elements of that lattice, which are rectangular partitions, which can be indexed by pairs of positive integers. This representation allows saturated chains in the lattice of partitions to be represented as tableau by assigning sequential integers to elements of the base set of pairs of positive integers. Birkhoff's representation theorem is a beautiful classical result. Representation is constructed by first identifying the joint irreducible elements of the lattice, those that cannot be expressed as the joint of smaller elements. The joint irreducible elements are the elements that cover exactly one element. On the left, the lattice has 4 joint irreducible elements shown in green. The joint irreducibles inherit a partial order of the lattice, as shown in the center. On the right is the lattice ideals of that coset, showing that the original lattice is isomorphic to the lattice of ideals of the coset of joint irreducibles. Any saturated chain in this lattice can be represented by numbering the subset of joint irreducible elements compatible with their coset ordering.
Wait, went backwards. Did you hit something?
I must have hit something accidentally.
It's too tight.
Sorry about that. Trouble with non-distributed multiple modular lattices is that to recover the original lattice from the closed set of joint irreducibles, we must take only closed ideals of the closed sets with some particular closure operator. The closure operator captures the non-distributivity of the lattice. The meet of elements remains represented by the intersection of ideals, just as in the distributive case, but the join becomes the closure of the union of ideals rather than just the union. The fundamental task is to characterize these closure operators. The closure operator is characterized by which joint irreducibles it adds to any given set of joint irreducibles. This can be used to characterizing the minimal sets, which cause the closure to add each particular joint irreducible to the set. Permanent introduced dissecting a lattice into overlapping blocks. The blocks are the maximal complemented intervals. Here, the lattice in the center is the 4 blocks shown around it. The set of blocks is called the skeleton of the lattice. The skeleton inherits a lattice ordering from the lattice. The skeleton is shown in the upper right. The lattice that is then characterized by the blocks, the skeleton that orders the blocks, and exactly how each block overlaps with its neighbor blocks, called the gluing. 2 blocks are glued by identifying a filter of the lower block with an isomorphic ideal of the upper block. This identification generates a pair of adjoint maps between the 2 blocks. Typical adjoint maps are shown in the right. For modular lattices, blocks are modular and complemented. This means the blocks are products of projective geometries. Unfortunately, the incidence lattices of non-Argesian projective planes are possible factors for blocks, which means that any full characterization of modular lattices depends on the full characterization of projective planes. Here we see that 2 blocks of the example are isomorphic to the Boolean algebra of 2 atoms, which is the product of 2 projective points. The other 2 blocks are projective lines with 3 points each. And here we see that the non-distributivity of modular lattices comes from the existence of factors that aren't projective points. Characterizing the closure operator of the representation of modular lattice requires determining which joint irreducible elements are less than or equal to the join of a given set of joint irreducibles. This test can be done entirely within 1 block containing the join. The test result is unchanged by replacing all of the joint irreducibles involved by their joins with 0 of the block. The join of a joint irreducible atom of 1 block with the 0 of a higher block is either the 0 of the higher block or an atom of a higher block. This join is called the reflex of the atom in that block. Thus, the closure operator is determined by 2 things. One is the closure of sets of atoms within the blocks, which is determined by the projective geometry structure of the blocks. The other is the pattern of how joint irreducibles are mapped into their reflexes in higher blocks. And happy birthday, Richard.
Hi, thank you. I didn't put any math in the first slide because I thought I would have to walk from far away. But anyway, today I'm going to talk about some problem I've been working on with one of my grad students, Stanley. And this is about a variation of something called penny game. So penny game, in the original form, there are 2 players. The first player chooses a binary word of, say, length k, and then player B chooses another binary word of the same length. And then a coin is tossed repeatedly until one of the 2 words appears in consecutive position. right? So you may have the first player choose 0, 0, 0, the second player chooses 0, 0, 1, and then this is more than me. Okay, good. So then the coin is tossed. Let's say this is the outcome. And then at some point you see 1, 0, 0, so player B wins in this case. Okay, so it is known that no matter what binary word the first player chooses, the second player can always choose a word that will appear first with probability more than 1/2. So this is an example of a non-transitive game. So it's not like one word is the best, because no matter what word is chosen, the other player can choose a better word. And in fact, there is a very nice formula that John Conway gave, where for any two binary words, it describes the probability that the given word appears first. Okay, so our goal was to try to do something similar to this, where instead of binary words, you have permutations. So the setup for us will be that now player A chooses a permutation of length k, then player B chooses another permutation of length k, and now instead of a coin, you have something like continuous random variables, and they generate some sequence. For example, here, let's say there are continuous uniform in 0, 1, it doesn't really matter. But then you get a sequence of real numbers, and you look at the relative order, and that determines the permutation. So for example, here, this is the sequence you get from left to right. You get these three values that are in the same relative order as 2, 1, 3. So in this game, player A had chosen this permutation, player B had chosen this permutation, so player B wins. Okay, so a lot of the questions we're interested in is the same kinds of questions. This is a non-transitive game. Also, for two given permutations, what's the probability that one appears before the other? So turns out this problem relates to enumeration of permutations avoiding consecutive subsequences. So if we ask maybe a simpler question would be, you just have one pattern, one permutation of length k, and you want to know what's the expected time before you see it appear for the first time. So turns out that can be obtained by simply taking the exponential generating function for permutations avoiding that consecutive pattern and evaluating it at 1. So this is not very hard to see, but it's kind of a nice fact, because for some patterns, these generating functions are known. Not in general, for an arbitrary sigma, this is not known, but for short sigmas and for monotone patterns or certain non-overlapping patterns, this generating function is known, so then we can know the expected time before we see that pattern. So for example, for 1 to 3, it takes on average a little less than 8 tosses. And but maybe the harder question is, given two permutations, what's the probability that one of them appears before the other? So if we denote this by PR sigma tau, we don't have a general formula for this, but we can compute it in some cases. So for example, when the two patterns have length 3, we can compute the numbers, and there are some examples of the numbers we get. Here's an example for patterns of length 4, where you get 1/2, which makes it look like it's very easy. But it's actually, this is probably harder than the other two. So here we, there's no obvious reason why this should be 1/2, but we can show it is. And just so you get some idea for how this is not very intuitive, these are two patterns of length 3, 1, 2, 3, and 2, 3, 1, where the pattern 1, 2, 3 is more likely to appear first in a random sequence, but the expected time you have to wait for that pattern to appear is longer. So, and that's because it's a non-transitive game, also for permutation. Okay, so just to finish, there are some open questions. One, we would like to have an expression for these probabilities for arbitrary patterns, but we don't have a formula. Maybe a simpler question is just to characterize for which pairs of permutations you get that the probability of either one appearing first is 1/2. Another question is there a winning strategy for the second player? And we have a conjecture that if you have a permutation and you move the last entry to the beginning, then that other permutation will be more likely to appear first. And then even if we prove that this is a winning strategy, there's still the question of what's the optimal strategy, which we have no idea what the optimal strategy should be. Okay, thank you.
I'll be talking about something about hierarchy decomposition shortcuts and the combinatorial invariance conjecture. So this is joint work with Mario Brenti. And the combinatorial invariance conjecture tells you that if you take two elements in a crossover group, then the Kazan-Lusztig polynomial of those two elements should depend only on the Brouwer interval determined by the two elements as an abstract process. So if you have crossover group W1 and you have U1, V1 in the first group and W2, U2, V2 in the second group, if the Brouwer interval U1, V1 is isomorphic to U2, V2, then the two polynomials should be the same. So in fact, I'm happy Mark introduced Kazan-Lusztig polynomials and also the R polynomials. If you say R instead of Kazan-Lusztig, it's exactly the same conjecture. So you take two permutations UV in a SAN, U less than or equal to B, where this is Brouwer ordering, and you take a Z that is weakly between U and B. So what they note by BUB, the direct graph induced on the closed interval UV, so all permutations between U and B Brouwer order by the Brouwer graph. So I'll say that ZE or simply Z is a joint hydrogen decomposition if these three conditions are satisfied. So one is that Z join X exists for X in your interval UV. The second one is that every P in ZB spans hypercubes. And the third one that ZB is diamond closed in U. So the first condition is easy enough. It simply says that Z has a join with every other element in the interval. To understand the second ones, it's useful to color the edges blue and red. So I'll color the edges inside the subinterval blue and all the other ones red. So now condition 2, every P spans hypercubes. So to say that P spans hypercubes means that if this is an anti-chain in your interval, and you have a red edge from X side to P, then there should be a unique embedding from the directed Hasse diagram of a Boolean algebra of rank K, the cardinality of the anti-chain, to your Brouwer graph that maps the top of the Boolean algebra to P and the coatoms of the Boolean algebra to S1 SK. So here, for example, I have my U, my P, my Z, I have a P in here, I have these three elements, X1, S2, S3, they're pairwise incomparable, there are red edges, they go into P, then it means that I have to see that hypercube, which just appear, and I have to see exactly one of them. To say that this is diamond closed is much simpler. It says that you will never see in your color diagram something like this. You will never see a diamond with the top two edges blue and the bottom two edges red. So now take a joint hypercube decomposition. I'll call an element P between Z and B a shortcut if all the directed paths from U to P that are of minimal length contain no blue edges. They're made entirely of red edges. And this result here is something that was proved by several authors. So if you have UV in SN, U less than V, then there's at least one Z greater than U that is a joint hypercube decomposition. So these objects always exist in symmetry. So then the conjecture we have is the following. So take two permutations in SN, U less than or equal to V. Take a Z between U and P that is a joint hypercube decomposition. Then the R tilde polynomial, which is a very simple renormalization of the R polynomial, is supposed to be equal to the sum of all shortcuts of Q to the distance between U and P, distance in the Brouwer direct graph, times R tilde of P. So now this implies the combinatorial invariance conjecture, because if you take for Z a Z that is strictly greater than U, then P will be strictly greater than U, and so by induction you can assume that you know these polynomials, so you know that polynomial, and if you know the R tilde, as I was saying, you also know the Kazan-Lusztig. So we know this is true for all intervals in SN for n less than or equal to 6. It's true for intervals of Becker post 5 and for lattices. Here's an example. Here's your U and P. This is a rank 5 interval in a symmetric group. This interval has 9 joint hypercube decompositions, so I've chosen one, this Z here, painted in green and blue. I painted blue all the edges inside the subinterval CV. So now I look for the shortcuts. This is always a shortcut, and in this case, there's only one other one, this vertex painted green. And so now the formula says you should look at the distance between U and Z. It's 2 times the theta polynomial from Z to the top. It's a Boolean algebra of rank 3, it's Q cubed. In this case, the distance is 1. So it's Q, and then you blew up the theta polynomial from that in shortcut to be this rank 2 is Q squared. So that's our conjecture. There are 2 more conjectures. One by Williamson and co-authors, they give a procedure to compute the Castelluzzi polynomial, and one by Brenti and Gessel that is similar to this one, and there are no known implications with these conjectures. I think I could go on speaking for about an hour because there's no next slide. So, many happy events.